Example 6.3. A voltage of 1.2 volts will be applied to a 33-meter length of 20-gauge gold wire at room temperature. Calculate the current, magnitude of the current density, and the magnitude of the electric field within the wire. B. Calculate the resistivity if the gold wire is inserted into boiling water, where its coefficient of resistance is 0.00340 per degree Celsius. Let's sketch a picture here. So if I'm looking at a wire, then I'm seeing that a sketch of this 20-gauge gold wire. I imagine that I have my wire that's going to look like this. And if we imagine that it's just a wire, a physical wire, then we know, of course, that if it's gold, it's going to have this gold color. And then inside, I'm going to have ions. So I imagine that I have these gold ions throughout the wire. And now we're going to place a voltage drop across this. So if I place a voltage drop, that means on this end, this is going to be a potential of 1.2 volts. Over here is going to be negative, and this guy we then set to 0 volts. So they tell us two things about the wire. They tell us that it has a length of 33 meters, and it has a diameter that we're going to have to look up. So if I look this up, I'm going to have to Google stuff. So then if I Google a couple of quantities here, so I'm going to Google 20 gauge wire, and when I Google this, it tells me here that the diameter is equal to 0.914 millimeters. So if I look at this thing, it's going to be 0.914 millimeters. So that's my diameter. But that's really not the picture that I see if I'm talking about in the language of voltage. So if I'm looking at this in the language of voltage, I should have an incline. In other words, I have a incline that has to look something like this here. So if I do this, I imagine that now I have my wire. And my wire is coming up like this. And then at this height here, I have my positive plate at this height. So when I'm looking at this, I have my red plate and I have my ground plate right here. And so that means that up here, I'm going to have a positive charge. Down here, I'm going to have a negative charge. And this is where we defined our 0 volts. And when I look at this height right here is now my voltage of the wire, which is 1.20 volts. So then this is my wire. So when I'm looking at my wire, I, of course, have my nuclei or ions. And so now what happens? I'm going to put my charges in here. So if I go in here and I start looking at my charges are everywhere. And then as soon as I put that voltage on here, they start to move, right? All of these charges simultaneously start moving. You can't really see that. You have to kind of imagine this, but on the incline, we could see that they're sliding down the incline. They have no choice. And then, of course, they then start all the collision process that goes on. So I'm going to bring this guy over here. And I'm going to bring this Google thing down here. So these are two equivalent pictures. Okay, I prefer the one on the right. Now, another thing that we need to go after, since we're talking about gold, I have to look up the resistivity of gold. So now we're gonna, at the same time, I ended up Googling the gold resistivity at room temperature. In other words, I looked at the resistivity of gold at 20 degrees C, and I ended up getting a value of 2.44 times 10 to the minus 8 ohms meter. So now that I got a picture, I could then go in and calculate three things. So here we want to calculate the current, current density, and electric field. So if I look at the current density, we could see, excuse me, the current. So the current is given by the macroscopic form of Ohm's law. So the current here has to be the voltage across the wire divided by the resistance of the wire. But we know how to write down the resistance of a wire because that has to be the resistivity of gold times its length divided by the area, and we already know what the voltage is across the wire. So if I clean this up, because it's a wire, we know that it has an area of pi r squared, the voltage of the wire, divided by these two numbers that we've already talked about. So it's going to be the length times the resistivity of gold. So now if I plug in my values, I'm then going to see that I'm going to have the resistivity, which is 2.44 times 10 to the minus 8 ohms meter times its length divided into the area, which will be 1/2, but they gave us the diameter. So if I look at the diameter of this thing, it has to be 0.914 times 10 to the minus 3 meters squared. And then I have to multiply that times the voltage, which is here. So I didn't do dimensional analysis last time. I should have, but if I look at the meters, they all cancel out. So what I'm left with is units of volts per ohm. So if I compute this, I'm then going to get a number that reads 0.977 volts per ohm, but a volt per ohm is a volts divided by amps. So this is 0.977. Here's my volt, and this is a volt per amp. And you could see here is that the units of volt cancel out. So then I end up with the current of 0.977 amps, which is now the current of the wire. So now let's go on to the current density in the electric field. The current density and electric field are, well, the current density of gold has to equal to the current of gold divided by the area. So if I just plug in the values that we just got, it would be pi times 1/2, 0.914 times 10 to the minus 3 meters squared. And then the current that we just computed is 0.997 amps, and I get a value that then reads 1.49 times 10 to the 6 amps per meter squared. And if I look at the electric field of the wire, then it has to be the voltage of the wire divided by its length. So in this case, it's going to be 33.0 meters divided into 1.20 volts. So you could see here that this guy is going to be 0.364 volts per meter. So just as a check, I should get back the resistivity that we Googled. So as a check, if I take the electric field of the wire, and if I take the current density of this, and I look at the ratio of these, I do get 2.44 times 10 to the minus 8 ohms meter, which is, of course, the exact same value for the resistivity of the gold. Of course it is. It has to be that way. So now let's go on to the next section here. So now what's happening here is that the gold wire is inserted into boiling water. And of course, boiling water is at 100 degrees C and allowed to reach an equilibrium state. What that means here is that the voltage and current across this wire now reaches its final value. So then the question is, what is the resistivity at 100 degrees C of this gold? We would expect it to increase. Okay, we expect it to increase. So here's what we know. The resistivity goes something like this. So it starts at room temperature which is 20 degrees C, and reaches its final state at 100 degrees C. So that means here is that the resistivity has increased because the gold ions have increased their micro kinetic energies. And what we said earlier in lecture here is that if I have a resistivity of temperature T, it's equal to the resistivity at room temperature times a quantity 1 plus alpha delta T here, where rho initial is the resistivity of gold at 20 degrees Celsius, and alpha, which is called the temperature coefficient of resistance, maybe bring it down here, alpha, which is the temperature coefficient of resistance. And in this situation, it's equal to 0. I think I gave that value. It's 0.0340 per degree Celsius. And when I look up, we already know what the resistivity of gold is because we Googled it. So this is 2.44 times 10 to the minus 8 ohm meter. So now we can calculate the resistivity. So the increase in resistivity is then the resistivity at 100 degrees C is then going to be the resistivity at 20 degrees C times the quantity alpha times delta T. So if I plug in my numbers, then this is going to be the resistivity at room temperature, which will be 2.44 times 10 to the minus 8 ohms meter, times the quantity 1 plus alpha, 0.00340 per degree Celsius, times the change in temperature. So the change in temperature is then 100 degrees C minus 20 degrees C. And if I compute this number here, I have a value of 3.27 times 10 to the minus 8 ohms per meter. So this is the resistivity of gold. Let me move back this off just a little bit at 100 degrees C. So this is what that is. Again, these numbers, unless you don't use them, unless you use them a lot, are meaningless. So what does this mean here? That means the increase in resistivity is then looked at as the ratio at 100 degrees C to 20 degrees C. And so if I start to look at this, this will be 3.27 times 10 to the minus 8 ohms meter, whereas at room temperature, it's 2.44 times 10 to the minus 8 ohms per meter, which is then 1.34. In other words, this is a 34% increase in resistivity. That's a big jump. By the way, that also tells us that it's going to be a 34% increase in resistance.